Dear students, in this video we are going to study about Gauss law and its applications, electric flux for uniform electric field, electric flux through an arbitrary area kept in non-uniform electric field, electric flux for closed surfaces. Next, we are going to study about Gauss law and its applications, where we are going to study about E due to an infinitely long charged wire, E due to charged infinite plane sheet, E due to two parallel charged infinite sheets, E due to a uniformly charged spherical shell. Let us study about Gauss law and its applications. Electric flux. The number of electric field lines crossing a given area kept normal to electric field lines is called electric flux. And it is denoted by letter phi E, and its unit is given by Nm squared c power minus 1. Electric flux is a scalar quantity and it can be positive or negative. And for simpler understanding of electric flux, this diagram is very much useful. So here in this case the electric field of a point charge plus q is drawn, and consider two small rectangular area elements A and B placed normal to the field. Even though these elements have the same area, the number of electric field lines crossing the element in region A is more than that crossing the element in region B. Therefore, the electric flux in region A is more than that in region B. Since electric field strength for a point charge decreases as the distance increases, the electric flux also decreases as the distance increases. The above discussion gives a qualitative idea of electric flux. However, a precise definition of electric flux is needed. Next, we are going to study about the electric flux for uniform electric field. For this, consider a uniform electric field in a region of space, and let us choose an area A normal to electric field lines as shown. The electric flux for this case is given by the expression phi equal to EA, and suppose the same area A is kept parallel to the uniform electric field, then no electric field lines pass through the area A as shown here in 1.31b. This one, and the electric flux for this case is 0. So the expression phi E is equal to 0. If the area is inclined at an angle theta with the field, then the component of electric field perpendicular to the area alone contributes to the electric flux. The electric field component parallel to the surface area will not contribute to the electric flux. And that is shown in this diagram 1.31c. Then for this case, the electric flux is given by phi E equal to E cos theta times A, where this theta is the angle between the electric field and the direction normal to the area. In general, for uniform electric field, the electric flux is defined as phi equal to E dot A, that's given by EA cos theta. Here we should note that area vector A is given by A dot A times n cap, and its magnitude is simply the area A, and its direction is along the unit vector n cap perpendicular to the area as shown. Using this definition for flux, phi equal to E dot A, and the equations 1.53 and 54 can be obtained as special cases. In the figure 1.31a, theta equal to 0, therefore phi equal to E dot A, and that's given by EA. In figure 1.31b, theta is given by 90 degrees, therefore phi equal to E dot A, and that's equal to 0. So in these diagrams represent the position of the plane and the angle between the electric field and the plane. Next, we are going to study about this electric flux through an arbitrary area kept in a non-uniform electric field. Suppose the electric field is not uniform and the area A is not a flat surface. Then the entire area can be divided into n small area segments, delta A1, delta A2, delta A3, and so on, such that each area element is almost flat and the electric field over such area element can be considered uniform. The electric flux for the entire area A is approximately written as phi equal to E1 dot delta A1 plus E2 equal to delta A2, and so on. That's given by summation I equal to 1 to n times EI dot delta AI. By taking the limit delta I tending to 0 for all I, the summation in equation 1.56 becomes integration. So the total electric flux for the entire area is given by phi E equal to integration of E dot dA, and this equation, from this equation it is clear that the electric flux for a given surface depends on both the electric field pattern on the surface area and orientation of the surface with respect to the electric field. Next we are going to study about the electric flux for closed surfaces. In the previous section, the electric flux for any arbitrary curved surface is discussed. Suppose a closed surface is present in the region of the non-uniform electric field as shown in this 1.33a. Then the total electric flux over this closed surface is given by phi E equal to closed integral of E dot dA. Here you should note the difference between the equations 1.57 and 1.58. The integration in equation 1.58 is a closed surface integration, and for each aerial element the outward normal is the direction of dA as shown in figure 1.33b here. Then the total electric flux over a closed surface can be negative or positive or 0. In figure 1.33b, it is shown that in one area element the angle between dA and E is less than 90 degrees. Then the electric flux is positive, and in another aerial element the angle between dA and E is greater than 90 degrees. Then the electric flux is negative. In general, the electric flux is negative if the electric field lines enter the closed surface and positive if the electric field lines leave the closed surface. Next, let us study about Gauss law. For this, let us consider a positive point charge Q is surrounded by an imaginary sphere of radius r, as shown in the diagram. We can calculate the total electric flux through the closed surface of the sphere using the equation 1.58, and phi E is given by closed integral of E dot dA that's equal to closed integral of E dA cos theta. The electric field of a point charge is directed radially outward at all points on the surface of the sphere. Therefore, the direction of the area element dA is along the electric field E and theta equal to 0. So the expression phi E is given by closed integral of E dA since cos 0 equal to 1. And these are the diagrams representing the Gaussian surface, spherical Gaussian surface, and here this is arbitrarily shaped surface. So this will give you the total electric flux of point charge plus Q, and this is the net electric flux that will be remaining the same through all the surfaces. Here E is uniform on the surface of the sphere, so phi E equal to E times closed integral of dA. Substituting for closed integral of dA equal to 4 pi r square and E equal to 1 by 4 pi epsilon q by r square in the equation 1.60, we get phi E equal to 1 by 4 pi epsilon q by r square into 4 pi r square. That's given by 4 pi into 1 by 4 pi epsilon q, so phi E equal to q by epsilon r, and this equation is called as Gauss law. The remarkable point about this is that the equation 1.61 is equally true for any arbitrary shaped surface which encloses the charge Q, as shown in the figure 1.35. We've seen that the total electric flux is the same for closed surfaces A1, A2, and A3, as shown in figure 1.35. Then Gauss law says that if a charge Q is enclosed by an arbitrary closed surface, then the total electric flux phi E through the closed surface is given by phi E equal to closed integral of E dot dA that's equal to Q enclosed by epsilon naught. But this Q enclosed denotes the charges within the closed surface. Now discussion of Gauss law. First case, the total electric flux through the closed surface depends only on the charges enclosed by the surface, and the charges present outside the surface will not contribute to the flux and the shape of the closed surface, which can be chosen arbitrarily. The second case, the total electric flux is independent of the location of the charges inside the closed surface. And then the third one is, to arrive at the equation 1.62, we have chosen a spherical surface. This imaginary surface is called a Gaussian surface. The shape of a Gaussian surface to be chosen depends on the type of charge configuration and the kind of symmetry existing in that charge configuration. The electric field is spherically symmetric for a point charge, therefore spherical Gaussian surface is chosen. Cylindrical and planar Gaussian surfaces can be chosen for other kinds of charge configurations. Next, fourth case, in the LHS of equation 1.62, the electric field E is due to charges present inside and outside the Gaussian surface. But the charge Q enclosed denotes the charges which lie only inside the Gaussian surface. Next, we are going to study about the applications of Gauss law. The electric field due to any arbitrary charge configuration can be calculated using Coulomb's law or Gauss law. If the charge configuration possesses some kind of symmetry, then Gauss law is a very efficient way to calculate the electric field. It is illustrated in the following cases. The first case, the electric field due to an infinitely long charged wire. For this, let us consider an infinitely long straight wire having uniform linear charge density lambda, where this lambda is called charge per unit length. Let P be a point located at a particular perpendicular distance r from the wire. The electric field at the point P can be found using Gauss law. For this, let us choose two small charge elements A1 and A2 on the wire which are at equal distances from the point P. The resultant electric field due to these two charge elements points radially away from the charged wire. The magnitude of electric field is same at all points on the circle of radius r, and that is given in this diagram here. Now, since the charged wire possesses a cylindrical symmetry, let us choose a cylindrical Gaussian surface of radius r and the length L as shown in one diagram 1.37, this one. The total electric flux through this closed surface is calculated as follows: phi equal to closed integral E dot dA, that's given by EdA integral closed surface EdA plus EdA plus EdA. So it is seen from that figure 1.37 that for the closed surface E is parallel to A and E dot dA equal to EdA. For the top and bottom surfaces, E is perpendicular to A and E dot dA equal to 0. Substituting these values in the equation 1.63 and applying Gauss law to the cylindrical surface, we have this equation 1.64 that's given by pi equal to closed surface EdA equal to Q enclosed by epsilon r. Since the magnitude of electric field for the entire closed surface is constant, E is taken out of the integration and Q enclosed is given by Q enclosed equal to lambda L, where lambda is the linear charge density, that is given by charge present per unit length. So E into closed surface dA equal to lambda L by epsilon r. Here, this closed surface integration dA is given by total area of the closed surface, that's given by 2 pi RL. Substituting this in the equation 1.65, we will get this equation 1.66, that is given by E equal to 1 by 2 pi epsilon r lambda by r, which can be represented in vector form like this: E vector equal to 1 by 2 pi epsilon r lambda by r into r unit vector. The electric field due to the infinite charged wire depends on 1 by r rather than 1 by r square, which is for a point charge. So the equation 1.67 indicates that the electric field is always along the perpendicular direction or cap to wire. In fact, if lambda is greater than 0, then E points perpendicularly outward from the wire, and if lambda is less than 0, then E points perpendicularly inward. This minus r unit vector. That is r cap. This equation 1.67 is true only for an infinitely long charged wire. For a charged wire of finite length, the electric field need not be radial at all points. However, the equation 1.67 for such a wire is taken approximately true around the midpoint of the wire and far away from both the ends of the wire. Next, in the second case, let us study about the electric field due to charge the infinite plane sheet. For this, let us consider an infinite plane sheet of charges with uniform surface charge density sigma, where the sigma is called charge present per unit area. So let P be a point at a distance r from the sheet as shown in the figure 1.38, this one. Since the plane is infinitely large, the electric field should be same at all points, equidistant from the plane and radially directed outward at all points. A cylindrical Gaussian surface of length 2r and two flat surfaces each of area A is chosen such that the infinite plane sheet passes perpendicularly through the middle part of a Gaussian surface. Total electric flux linked with the cylindrical surface is given by this expression 1.68 phi equal to closed integral of E dot dA, that's given by Q enclosed by epsilon naught. Electric field is perpendicular to the area element at all points on the curved surface and is parallel to the surface areas at P and P dash. Then applying Gauss law to this equation, phi E equal to integral EdA plus integral EdA. These are integrated at the points P and P dash for the surfaces. That's given by Q enclosed by epsilon naught. Since the magnitude of the electric field at these two equal flat surfaces is uniform, E is taken out of the integration and Q enclosed is given by Q enclosed equal to sigma A. So we get 2E times integration P dA equal to sigma A by epsilon naught, and for the total area of the surface either at P or P dash, the expression for electric field is given by sigma by 2 epsilon naught. So in vector form we can write like this: E vector equal to sigma by 2 epsilon naught n cap. Here n cap is the outward unit vector normal to the plane. Note that the electric field due to an infinite plane sheet of charge depends on the surface charge density and is independent of the distance r. The electric field will be the same at any point further away from the charge plane. So the equation 1.71 implies that if sigma is greater than 0, the electric field at any point P is along outward perpendicular n cap drawn to the plane. And if sigma is less than 0, the electric field points inwards perpendicularly to the plane. For a finite charge plane sheet, the equation 1.71 is approximately true only in the middle region of the plane and at points far away from both ends. Next we will consider the third case, where we are going to find out the electric field due to two parallel charged infinite sheets. For this, let us consider two infinitely large charged plane sheets with equal and opposite charge densities, plus sigma and minus sigma, which are placed parallel to each other as shown. The electric field between the place and outside the place is found using Gauss law. The magnitude of the electric field due to an infinite charge plane sheet is sigma by 2 epsilon naught, and it points perpendicularly outward if sigma is greater than 0 and points inwards if sigma is less than 0. At the points P2 and P3, the electric field due to both plates are equal in magnitude and opposite in direction. As a result, the electric field at a point outside the place is 0, but between the plates, the electric fields are in the same direction, that is towards the right, and the total electric field at a point P1 is given by E inside, is given by sigma by 2 epsilon naught plus sigma by 2 epsilon, that's given by sigma by epsilon naught. So the direction of the electric field between the plates is directed from positively charged plate to negatively charged plate and is uniform everywhere between the plates. Next, fourth case, electric field due to a uniformly charged spherical shell. Consider a uniformly charged spherical shell of radius r carrying total charge q as shown. The electric field at points outside and inside the sphere can be found using the Gauss law. First, let us consider a case in which the point lies outside the shell, such that r is greater than capital R. Let us choose a point P outside the shell at a distance r from the center as shown. The charge is uniformly distributed on the surface of the sphere, so it is called spherical symmetry. Hence, the electric field must point radially outward if Q is greater than 0 and point radially inward if Q is less than 0. So, a spherical Gaussian surface of radius r is chosen, and the total charge enclosed by this Gaussian surface is given by Q. So, applying Gauss law, you have this Gaussian surface integral E dot dA equal to Q by epsilon naught. The electric field E and dA point in the same direction outward normal at all points on this Gaussian surface. The magnitude of E is also the same at all points due to the spherical symmetry of the charge distribution. So the equation can be written as E Gaussian surface closed integral dA equal to Q by epsilon naught. But this integration dA is equal to total area of the Gaussian surface that's given by 4 pi r squared. So substituting this value in the equation 1.74, you have that is E is equal to 1 by 4 pi epsilon naught Q by r square from these two expressions. Next, in vector form, this same equation can be written as E vector equal to 1 by 4 pi epsilon Q by r square r cap. Electric field is radially outward if Q is greater than 0 and radially inward if Q is less than 0. From the equation 1.75, we inferred that the electric field at a point outside the shell will be the same as if the entire charge Q is concentrated at the center of the spherical shell. Next case B, at a point on the surface of the spherical shell. We are considering a point on the surface of the spherical shell. So R is equal to R. The electric field at points on the surface on the spherical shell R is equal to R is given by E equal to Q by 4 pi epsilon naught R square or cap. This is the equation. Now you can consider a point inside the spherical shell such that R is less than capital R. For this, let us consider a point P inside the shell at a distance R from the center, where a Gaussian sphere of radius R is constructed as shown. Applying Gauss law, we have integration of E dot dA equal to Q by epsilon naught. So E into 4 pi R square equal to Q by epsilon naught. Since Gaussian surface encloses no charge, Q is equal to 0. So the equation 1.77 becomes E equal to 0 for the case R less than capital R. And the electric field due to uniformly charged spherical shell is 0 at all points inside the shell. So a graph is plotted between the electric field and radial distance. And that is given in this diagram, electric field versus distance for a spherical shell of radius R. Dear students, Gauss law states that if a charge Q is enclosed by an arbitrary closed surface, then the total electric flux phi E through the closed surface is given by the expression phi E equal to closed integral of E dot dA, and that's given by E enclosed by epsilon naught.